So in order to get an idea how neural networks are trained, we'll use a very simple neural network in Python. So first of all, let's recap how the so-called feed-forward path of a feed-forward network is computed. Remember that you have an input vector x and a label vector y. Especially in the case of classification, y is a vector. For regression, y is often a scalar, but for the math it doesn't matter since we are working with vectors and matrices anyway. So the task of a neural network now is to compute y hat from an input vector x, using the weight matrices w1 and w2, such that y hat and y are as close as possible for all vectors in the training set x. Let's actually have a look at the math. So to compute from left to right, the first thing you do is multiply x by w1 to obtain c2. Since we are squashing intermediate layer calculations with activation functions, we have to apply the activation function to c2 to obtain a2. Then we compute the output layer, so note that we are multiplying a2 by w2. This is some sort of stacking the computations on top of each other. And finally we compute y hat by applying the activation function to c3 and we are done. So our weight matrices w1 and w2 are still randomly initialized. Therefore y hat and y are different. So now we have to train this neural network to do a better job. And training basically means updating the weights in order to obtain the best y hat on a given x with respect to y for all data points in x. But how do we find the optimal values for the weights? This is the plot, our two weight values and the cost. So the cost basically tells you how good or bad your weights are chosen. The lower the cost, the better the neural network performs. The cost function is called j. Note that it depends on w and t. So w is the weight matrix of the neural network. This is the one we want to optimize over. And t stands for the training dataset, which stays always the same. Therefore j is only dependent on w. This is a two-dimensional example, but in reality this so-called optimization space is very high-dimensional and impossible to plot. So how can we now find good values for w? Of course we can check every possible combination of values for w, or can't we? So one way of doing this is called grid search. So in this example we choose a discrete set of values within w1 and w2 and just apply the cost function j to all of those combinations, and the one combination with the lowest cost is an optimal value set for w. Now imagine that each individual scalar weight can be assigned to a value between -1 and 1. Now we create a grid over this continuous range with a step size of 0.1. So this basically forms a grid, therefore the method is called grid search. And now imagine we have only a single scalar weight value to optimize over. So we have to test 21 individual values. If we add one more weight, we already have to test 411. In 3 dimensions we are on 9,261 combinations. In 4 dimensions we already have to test and compute 194,481 values. And as we see, this number keeps growing exponentially. With only 100 dimensions you have to test more combinations than there are atoms in the universe. So this obviously is not a good way for neural network training. So what if we not strictly follow a grid and just randomly select value combinations for the weights? So it turns out that this method, which is called Monte Carlo, outperforms grid search. But still, in order to get a good approximation of the cost function, we need to test a lot of values, which is not feasible for neural network training. So what if we had a possibility when evaluating a single value to know in which direction we should go in order to test for the next value? We then could climb down the ladder one step by another until we reach the optimal value. This method is called gradient descent, and with all its variants, it's the de facto standard for neural network training. So how does this work? Let's have a look at our cost function j. In this case the so-called quadratic cost, which basically sums the squares of the differences between the prediction of the neural network and the actual real value. This difference is called error. Therefore, this is also called the sum of squared errors. There exists other cost functions as well, like cross entropy, exponential cost, Hellinger distance and many more. Choosing an appropriate cost function depends on your data and neural network topology and is part of the so-called hyper or meta-parameter space. An ideal selection is often considered as black magic. In other words, trial and error. So if we now have a look how y hat is calculated, we notice that this is dependent on the activation function f and on C3. C3 is calculated by the activation of the previous layer multiplied by the weights of the actual layer. If we replace the 2 by its definition, we obtain the following form. And if we replace C2, it's x multiplied by the weights of layer 1 and we obtain this form. Finally, we put this form into J and we obtain the cost function J based on all individual computations of the forward path of a neural network. So now we will use the so-called backpropagation method. This calculates the neural network computations backwards and it does so by backpropagating the error y minus y hat. Intuitively, this means that on the reverse computation of the neural network, big weight values end up in backpropagating big amounts of the error to the upstream layers, whereas small weight value only lets small amounts of the error being backpropagated. So let's assume on a given data row we end up with a certain amount of error indicated by the red circle. So if we now backpropagate this error, we use the weight to determine how much of this error should be backpropagated. Since the weight is high, we also increase the error, which then gets backpropagated. Now if the weight is small, the error also gets reduced. And the amount of error for that particular backpropagation to the upstream layer neuron is less. This is the desired behavior since big weights are contributing more to the overall error than small weights. So this is nice, but what we actually want is not the error or cost on each neuron, but the gradient of each error. If we know the gradient, we know in which direction we have to update each weight in order to go downhill the cost hypersurface. Therefore, we compute the partial derivative with respect to W2 first. I'll skip the linear algebra and calculus here, but it turns out that the derivative is A2 transpose times delta 3, which is based on the reverse computation, which is also called backpropagation. So note that f prime is the first derivative of the activation function f. Now we continue in backpropagating the error and taking the first derivative of that function in parallel to obtain delta 2. And finally, we get the partial derivative with respect to W1. And again, the mathematical reason why this is computed using the transpose of x times delta 2 is beyond the scope of this course and due to the chain rule in calculus. So as you have seen, training a neural network can get quite complicated. But it's okay if you didn't understand all the details. Just note that gradient descent doesn't make any guarantees that it converges to the global optimum unless the cost function is convex, which is not the case in neural networks. So it might get stuck in local optimas and even hasn't any guarantees to converge at all. Therefore, a lot of hyperparameter tuning might be necessary. In the next module, we will cover TensorFlow, one of the hottest deep learning frameworks out now.